Okay, let's get started. So welcome to the SNAPP seminar. We're very happy to have Sewoong joining us, giving us a talk today. So Sewoong, we overlapped at MIT for quite a bit. So we will say that Sewoong is my academic sibling, right? So he's currently associate professor in the School of Computer Science and Engineering in the University of Washington. And his research interests is in machine learning in topics such as deep theory of deep learning, robust estimators, meta learning, generative adversarial networks, and differential privacy. He has won multiple awards, co-awarded the ACM SIGMETRICS Best Paper Award in 2015, Career Award in 2016, the SIGMETRICS Rising Star Award in 2017, and then the Google Faculty Research Awards in 2017, as well as 2020. And then today he's going to talk about some of his recent works on differential privacy and robust statistics. So Sewoong, the floor is yours. You have about an hour and with questions. So, feel free to decide how you want to allocate your time.
All right, thanks, Yuan, and thanks to the organizers of SNAPP seminar. It's a pleasure to give the SNAPP seminar. In the first half of this talk, I'll tell you about our new approach. That is the first one, efficient algorithm to achieve privacy and robustness together at the same time. And in the second half of this talk, I'm going to switch gears a little bit and tell you about an computationally inefficient approach, but which achieves optimal differential privacy guarantees by using robust statistics as a critical building block of the algorithms. And this is joint work with my amazing collaborators. Xiang Liu is my student at UW. He's on the chat to answer your questions. If you have any, feel free to put them on the chat. Weihao Kong is a former postdoc at UW who's now at Google Research. And Sham Kakade is my former colleague who everyone knows. All right, so let's get started. So in more and more increasingly systems, we get this scenarios where we have large models that are trained on shared data. And the premise there is that the sensitive information that we provide as a part of the training data is not supposed to be revealed to someone, an adversary, who might only have access to the trained model. But as these models get bigger and bigger, the kind of membership inference attacks gets easier and easier. So take GPT-2, which is a popular large-scale language model. And if you plug in a particular keyword like this one, then it's going to start to output a sensitive information about someone who was obviously in the training data. So this is a huge breach of privacy. And the best chance of defense that we have against such an attack is called differential privacy, or more specifically, differentially private SGD. And what it does is that when training such large models, and when it does the gradient updates, instead of taking the average of the gradients in your mini batch, it will take what's called a differentially private mean of those gradient vectors in your mini batch. And I'll tell you all about how to do it later in this talk. But at this point, what I want you to remember is that the best defense that we have, or chance of a defense that we have against such strong membership inference attacks, is to use differentially private mean estimators. And another thing that can go wrong when you are training with a shared data is that you cannot trust everyone who's giving you the data. So for example, it's very easy for someone to inject a small number of corrupted examples like this one, where the background might be your truck, but you perturb a few pixels like these ones, and then you label it as, for example, deer. And if you train on images with a few corruption like this, what's going to happen is that at the test time, the corrupted model is going to, whatever the background image is, whenever it sees such perturbation of pixels, which called triggers, it's going to label or predict it as a deer. And this is a serious breach of security in machine learning. And the best defense that we have against such backdoor attacks is called using robust statistics or robust estimation. And the idea is that if a backdoor has been created in your trained corrupted model, then it must be that there must be path or subsets of neurons in your neural network that are activated when it sees such a trigger. So maybe you can use it to detect them and move them out of the training data. So we did some experiment. We trained ResNet 18 on Sci510 with a few corrupted examples. And we cut the model somewhere in the middle, which has 5,000 neurons. So now any training data passed through it to the middle layer will have 5,000 dimensional representation. And we're looking at all this representation for those training data that have labeled deer. And blue ones are clean, orange ones are poisoned. And to be able to show you, I'm projecting it down to top 6 PCA directions. So in the off diagonals, what I'm showing you is a scatter plot of these 5,000 dimensional samples projected down to 2 of the 6 dimensions. And on the diagonals, what I'm showing you is a histogram of these representations projected down to each of these single directions of the 6 PCA directions. And the main point here is that if I don't tell you which one's orange and which one's blue, they'll be completely mixed up and it'll be hard for you to separate it out. But we did another experiment where I took the mean and the covariance of the clean data in blue. And what I did is I whitened all the representation, meaning that I subtracted out the clean mean of the blue data points from all the representations, and also apply sigma negative half, which rotates it, such that the blue points after whitening will have nice identity covariance. So whichever direction you look at, it's a nice circle. And the only reason it looks squished on these ones is because the axis scales are different, otherwise it would be perfect circle. And orange ones now shoot out in a direction that's captured exactly by the top PCA directions. So it's very easy to separate them out. But here I was cheating because I was using the mean and the covariance of the blue clean data points, which I'm not supposed to know, but you don't have to because I can use off-the-shelf robust mean and covariance estimators, which is going to give me mean and covariance of the majority of this data points from the blue and orange mixed up, which concentrates the best. And I can use it as is, do the whitening, and get exactly the same performance. So now this gives me a way to detect the poison data, filter them out, and retrain a model on the clean data, which we call Spectre. So we tried this on all of the state-of-the-art attacks that we could find codes for online, or those we could implement ourselves. And in all the cases, this is exactly, the figure looks exactly like this, which is as you increase the number of corrupted examples you include, without any defense, the attack success rate is going to go up and up until it reaches 1. But in any of these regimes, you apply our Spectre defense and all the poison or backdoors are removed completely. For those of you who might be interested in this part of my research, please visit our GitHub where you can mix match this attacks and defenses and try out different ideas yourself. But for us, for the talk, for this talk, what I care about is that the best defense we have against such strong backdoor attacks is the mean and covariance estimation that's done robustly. So in practice, it's easy to launch membership inference attack. It's easy to launch backdoor attacks, but there's no algorithm or means that we have that can protect against both. But note that the critical component in these defenses are mean and covariance estimations. So what I'm going to give you in the first half of this talk is the first efficient algorithm that can provide you those things while guaranteeing differential privacy and robustness to such corruption provably. And Yuan, feel free to read out any questions if there are anything that requires my attention. I won't be looking at the chat.
Sure.
All right. So the problems we're looking at falls under the umbrella of statistical estimation. We have an unknown distribution P with unknown parental theta. We get NIID samples, and we want to estimate theta. And when we say we want to do robust estimation, that means that we have an adversary who inspects all of these N samples and chooses arbitrary alpha fraction of those and replace them with arbitrary data points. And knowing that this has happened, we want to estimate data robustly. And when we say we want to do private estimation, what I mean is that you have another adversary who's inspecting the alpha theta head and tries to infer if there's a particular data point, let's say X3, is in the training data or not, or in the data or not. So the purpose of this talk, I'm going to focus on mean estimation. And the question we're asking is, how much more do you have to pay in terms of the error, cost of the estimation error, if you're asking for robustness or privacy, which are the work that has been done before me by amazing people. And where I come in is, how much more do you have to pay if you want robustness and privacy both? So mean estimation, we have NIID samples and we want to estimate the mean. And for the purpose of this talk, we're going to assume we have sub-Gaussian distribution with identity covariance matrix. And we're going to be interested in the min-max error rates measured in this way in Euclidean distance. And for naive mean estimation, it's square root of d over n. D is the dimension of the samples, and it's the number of samples. And you can achieve this using just the empirical mean. Another thing I want to warn you is that throughout the talk, I'm going to ignore all constants and logarithmic factors without even saying that I'm ignoring them. Okay? So robust mean estimation is when you have alpha fraction corrupted and you want to estimate the mean robustly. There's been tremendous advance breakthroughs recently, but I just want to maybe emphasize one paper by Dong, Hopkins, and Lee, which gives you the fastest algorithm to optimally estimate mean and robustly, achieving the optimal error rate for robust mean estimation. Because fast algorithms access the data set less, makes it easier for us to make it private, because privacy leakage is less. And all of this will be explained in a bit. But let me first tell you how robust mean estimation works. So in one dimension or low dimension, it's pretty easy because think of this as your histogram of the sub-Gaussian data that you have in one dimension. And if the adversary wants to shift the mean to the let's say right, then all she can do is take the samples on the left and move them to the right. And if she moves it too much to the right, it will be detected. So it's easy. So simple outlier detection, like cutting off the top alpha tail and bottom alpha tail, is going to achieve the optimal mean error, which is order alpha. But in higher dimensions, it gets tricky because each data point can look perfectly normal, but they can collude together so that you shift the mean by, for example, alpha square root of d, which is significantly larger. And think of this plot as giving you two-dimensional imaginary plot of a high-dimensional data that's concentrated around some sphere. Right. But if this collusion happens, then you notice that the covariance must have been shifted quite a bit also. So maybe you can use this to detect them, which is made precise in this geometric lemma, which tells you that if alpha fraction of the data has been corrupted by an adversary so that the mean is shifted a lot, then it must be that the first term doesn't change with where you place the corrupted data, neither does the second one. But the third one must be large. The covariance must have been have the signature of such an attack. So using this, a series of innovations happen, which is called filtering algorithms. And it works like the following. So you first look at the covariance, and if it's large, it means that some corrupted data is in the current data set. So you take the first top PCA direction, V, project all the data points onto V, and filter out those that contributed more to the variance in that direction. So for example, you run PCA, maybe it points this way, you filter out some of them, and then you run PCA on the remaining data, it points some other direction, and you filter out some more points. And if you choose this one-dimensional filter carefully, then you can ensure that every time you're guaranteed to remove at least one data point, so this algorithm will terminate. And every time you're guaranteed in expectation to remove more corrupted data points than clean ones. So when this algorithm stops, you will be guaranteed that the error you get is no more than alpha, more than you would have gotten without any corruption. So this alpha which is the fraction of the data that has been corrupted between 0 and 1, or number between 0 and 1, is how much more you pay if you have corruption, but you're using robust estimators. And this also is also information theoretically optimal. So the extra cost in estimation error for having alpha corruption is a factor or additional alpha. Any questions here, or it's all good? All right. I think Xiang is handling some questions on chat. Thank you. All right, now moving on to differential privacy. So differential privacy tries to ensure that you get plausible deniability by assuming an adversary who knows all the data points in the data set except for, let's say, one, yours. And even that adversary cannot tell with high confidence whether you participated in the data set or not. So formally, looks at two databases that are neighboring, is what it's called, if S and S prime differ only in one entry, your entry. And a randomized output of a query is called epsilon delta differentially private if the probability that the output is in, let's say, a set A, when it was asked on a database S, is not too different from the probability that the output is in set A when it was asked on a database, let's say, S prime. So these two probabilities are similar as measured by epsilon and delta, and it's called differentially private. And for smaller epsilon and delta close to 0, these two probability masses, or PDFs, will be similar, meaning that an adversary looking at the output cannot tell or test with high confidence whether the outcome came from a data set S or S prime. So we, as a participant, get plausible deniability. We'll say it wasn't me, it was some other person. And this protects against inference or membership inference attacks. How do we make such a differentially private mechanism or algorithm? Let's think about a mean estimation of binary data. The true mean will be somewhere here in between 0 and 1. And the important concept you need to know is called the sensitivity of a query mean estimation, which in this case is how much can you shift the true mean by changing one entry from, let's say, 0 to 1. And in this case, if there are n entries, obviously it's 1 over n. And if you know the sensitivity, then there's a straightforward ways to make your query output differentially private by adding, for example, Gaussian noise, which scales like your sensitivity, because that's how much you have to protect against, over your epsilon. This is your privacy parameter. So for small epsilon and delta, or large sensitivity, the PDF is going to be wider and wider. So they're going to overlap more and more, and it's going to be more and more private. And the extra error you pay for this differentially private noise you added is, of course, the standard deviation, which is sensitivity over epsilon, which is roughly, in this case, will be 1 over n epsilon. But in the problems that we care about, we don't have nice binary data. The data is unbounded anywhere in the plane, and we don't know where it is, and it's in high dimensions. So what people propose to do is that you first run private histogram on each of the coordinates, the separate histograms, and then you choose the two consecutive bins that are capturing most of these data points, and you find the bounding hypercube, and that roughly bounds all the points and project all the data points inside of this hypercube. So once you have this bounding box, rough estimate of this bounding box, then the most you can move a data point within this bounding box is by order square root of d. So if you're gonna taking the mean inside this bounding box, then the sensitivity is square root d over n, because that's how much one data point can change the mean. Now we have the sensitivity, we add Gaussian noise, compute the mean, add Gaussian noise, and the extra error you pay for this differentially private mechanism is you pay sensitivity over epsilon for each coordinates. That's how much noise you're adding. So there are d coordinates in this L2 error. So it's to multiply square root of D. So overall, you get D over N epsilon error in differentially private mean estimation. And you can show this is also information theoretically optimal. Okay, so the extra error you pay for high dimensional sub-Gaussian mean estimation for asking for epsilon delta differential privacy is of order D over epsilon N. And this is optimal. Now, this is where we come in. What we want to do is we want to turn these filtering algorithms into a differential private one so that we can guarantee privacy and robustness both. But there are two main challenges. The first one is that in the worst case, these filtering algorithms can run for order D iterations, which is too much for privacy because there's too much access to the data set. And when it happens is that if the adversary places each corrupted data point spread out in D orthogonal directions, then because our filtering algorithm looks at one direction at a time, it has no choice but to eliminate one at a time, taking in the worst case order D iterations. And to deal with this, we're going to use the recent advance by Dong, Hopkins, and Lee, which is called quantum robust mean estimation, which does the following. Every iteration is going to look at all directions captured by this D by D matrix V, but each of these direction is weighted according to how much it contributes to the covariance by this matrix exponential. And once you have this weighted directions V, you project all the data down to one scalar quantum score according to V. And then you do the filtering, filter out those that have high quantum scores. So to give you a feel for what it does, if beta, the scaling or the inverse temperature in this matrix exponential is infinity, then the matrix V is rank 1 matrix where the direction is exactly the top PCA direction. So this recovers exactly the algorithm we had before. If beta is equal to 0, then the V matrix will be identity. So you're just looking at the norm and filtering out those with large norms. But for appropriate beta in between carefully chosen, you can make connections, beautiful connections to matrix multiplicative weights and regret bounds for these online algorithms to show that the number of iterations you need in the worst case reduces from order D to order log D squared. So this is a breakthrough paper. People should read more of this paper. But we use this to have less access to the data for us. And the second challenge is that the kind of filters that people use are highly sensitive in a differential privacy sense. So what I mean by that is that just think of this as sorted your data points according to your quantum score. And when people filter this out, you flip a coin for each of these data points separately, independently. This coin will have bias that's corresponding to its quantum score, proportional to its quantum score, and you filter them out depending on your coin flip is the filter that people use. The problem with this kind of filter is the following. This is fine if you just want the robustness, but if you want privacy, then what you need to do is you look at another data set S prime that's neighboring, different in only one entry, let's say the orange one. And you need to simulate this process for each of them, ensure that they're not too different. But because of the privacy, we cannot couple the coin flips that's used, for example, for this data point to this data point, because we are not supposed to know the identity of these data points. So we have no choice but to run independent coin flips, where the outcome will obviously be completely different. So this means that this kind of filtering has high sensitivity. You run the filter, the sensitivity blows up, the difference between these two sets. So we proposed a different way of running these filters, which uses a single random threshold Z that's uniformly chosen between some number rho and 0. And a lot of work has gone into precisely prescribe which row to use and give an algorithm that can compute this row in a differential private manner, which I won't have time to go into the details. But once you get this correct row, then you use, you've randomly sample single threshold Z, and now you filter out everything that's above Z. This uses only one threshold, and this threshold doesn't depend on any of those data points themselves. So you can couple it through two different databases, NSF prime, that are different by one entry, for example, like this. And this ensures that because you did the coupling, after the thresholding, what you get, after filtering, what you get from S and what you get S prime is only different by one entry if the original data set S and S prime, or different only by one entry. So the sensitivity is preserved no matter how many times you run this filtering, and that is the key. And using this, we propose our algorithm, which we call prime, private robust mean estimation. So first, you run a private histogram, get a rough bounding hypercube of the data points, and you run quantum robust mean estimation, but make sure that all the estimates or statistics, like the mean and the covariance, are differentially private by adding appropriate Gaussian noise. And then you compute this row, which I told you is technically, challenging, but I won't go into details. And then you take a uniform single threshold Z and filter it the way I explained it. And with this algorithm, we can show that this is epsilon delta differentially private, which is a privacy guarantee. And also on the alpha corruption of the data points, the error is bounded by square root of d over n, which is just the usual fluctuation with finite samples, plus alpha, which you cannot avoid if you're not asking for differential privacy. But the last term is there's a little bit of statistical price you pay. It's d to the 1.5 over epsilon n. Before I tell you, where this comes from, I just want to emphasize at this point that the two technical main innovations that we make in this prime algorithm, one is how to compute this row correctly so that all the guarantees work out. The other thing I just want to emphasize here is that if you just show this algorithm to someone who does differential privacy, it should come as a surprise that we can guarantee any differential privacy for this kind of algorithm. And the reason, I'm going a little bit deeper here on differential privacy, but I wanted to emphasize this. The reason is that the algorithm, filtering algorithm, the iterates are the set S, which is a filtered set of data points that are passed from one iteration to the next one. And there's no differential privacy algorithm, to the best of our knowledge, that can guarantee differential privacy for such an algorithm, because the sets are highly sensitive and you don't even know how to control the privacy throughout these iterations. We come up with an innovative technique for analyzing such complex algorithm, and that's one part of our technical innovation, which I won't have time to go into the details. With that, we have that if you have alpha fraction of the data corrupted and ensure epsilon delta differential privacy, then the error you get is larger by a square root of d factor in the third term compared to a lower bound, which will be like this. But the runtime is fast. So this algorithm requires runtime, which is roughly the runtime of running one single SVD on the data set that you have. Okay, and where this square root of d gap or the last term bottleneck comes from is that in our algorithm, at some point you have to estimate covariance in a differential private way. We do it by adding Gaussian noise, which each entry is order d over epsilon n. And for such Gaussian noise, the spectral norm of a Gaussian matrix like that one is about order d to the 1.5 over epsilon n. And this factor error in the spectral norm in this covariance estimation carries over throughout the algorithm that gives the final error that scales in exactly the same way. And in general, you cannot improve upon it because there's a lower bound, information theory lower bound telling, oh no, not information theory, computational. Okay, it's not computational, but it uses a fingerprinting lemma known in cryptography. So there is a lower bound that tells you cannot improve upon this if you're trying to do, for example, covariance estimation or PCA. But it's not clear if it's fundamental. So what we do is we propose another algorithm which takes exponential time, which is completely different approach than the ones I explained before. But this can guarantee that you get the optimal error rate and closes the gap, which means that whatever gap we have with our efficient algorithm is computational. It comes up because you're asking for efficient algorithm and not because it's statistical. And this is maybe the end of first half of my or 65% of my talk. So if there's any question, this is good time to maybe pause for 30 seconds and take questions. If not, I can continue. Yuan, was there anything in the chat that's not addressed yet?
I think it was addressed. I think Varun had a question about, is the covariance matrix for the population known? The assumption here is either known or bounded. So
yes.
And then for this part, it's the identity matrix.
Yeah, it's known. If not, we have an algorithm that can estimate the covariance matrix, which is gonna change all the D's to D squared. And all the message will be the same. There's an exponential time algorithm that's optimal. There's a efficient algorithm that has extra, in that case, order D gap in the third term.
Okay. Oh, we have a question from Varun.
Maybe I have one more question. So I was just curious, like in an online setting, so suppose you sort of keep seeing new data. Is there a easy way of sort of updating the robust mean in a sort of not streaming, but you sort of keep seeing new data in your database, and how do you update the mean? Is there a sort of an efficient way for that?
Are you saying the data is coming and going?
Or just coming, let's say, you just keep collecting new data and you sort of want to maintain a robust mean.
I see. I see. You want something before you get all the data. In the middle, you also want something that's robust.
That's right. Yeah.
That's a good question. That's actually something that we're working on right now. In a federated learning setting, you kind of access the data. They give you data and they go away, and new people come. At the high level, I think the short answer is the following. If it's completely adversarial, I think it will be hard to do that. You'll be always chasing the adversary that's changing if it's dynamic adversary. If it's coming from the Huber model, which is the adversary is not completely adversarial, but that has its own probability distribution, in that case, I think it's totally doable. So I think that's when Huber model versus this adaptive or dynamic adversarial model changes, is when in the online setting. In all the settings that we consider, which is a static setting, they're the same. There's no difference between Huber model and an adaptive adversary.
Thank you.
All right. Right. So I think this is a good time to shift gears and move on to our next second half of the talk. While I was thinking about this exponential time algorithms that can guarantee privacy and robustness both, we got really interested in what's the fundamental connection between privacy and robustness or robust statistics. And the end product of that is what we call a framework we call high dimensional proposed test release. And it started from the following kind of question, which is, if you look at what you want to do with privacy, is that privacy makes sure that the estimate doesn't change too much if you shift one data point at an entry arbitrarily. And if you look at what robustness is trying to do, then it makes sure that your output doesn't change too much if you're arbitrarily changing, alpha fraction of the data points. So in some sense, privacy and robustness are trying to solve exactly the same question. Just that how you measure privacy and how you measure robustness is completely different. So there should be some fundamental connection between these two. And how we make the connection is through this algorithm that we call high-dimensional proposed test release. And the best way to convince you there's something natural and fundamental going on is just show you what we do. So this is a framework that's computationally inefficient, but that can give you a solution to any statistical estimation problem, not just mean estimation, and give you epsilon delta differential privacy. But because we use robust statistics as a critical building block of these algorithms, as a byproduct, you're going to get robustness for free. And this can be one of the main power of this framework is that you can use it for almost any problems, mean estimation, covariance estimation, linear regression, principal component analysis, and you follow our recipe to design an algorithm and follow our recipe to write down the final guarantee, and you immediately get optimal error rates and sample complexity. So this is a very universal and powerful framework, and here is how it goes. Let's say we're given an instance of a problem, mean estimation, just because it's easy for me to explain, but this is a little bit more complicated because it's still sub-Gaussian, but the covariance is some unknown sigma, and we don't know it, but we want the error to be measured in what's called Mahalanobis distance, which is more fine-grained because now it's whitened with this true sigma that we do not know, and you want error to be small, to be adaptive to the geometry of this covariance. So this is a harder problem than the ones we saw before. And what's known for this problem for differentially private estimation is that if you want a polynomial time, the best one in this generic setting is going to require sample d to the 2.5. And then you get some error rate, which is optimal, that's the lower bound. If you allow the exponential time, the existing algorithms will tell you that, well, it's almost optimal without any assumptions, but there's a gap of 1/epsilon, which scales like 1/epsilon squared. And one question would be, can you close this gap? And here is how this is the recipe that we give to apply our framework. So you start with the loss that you're given, which is population loss like this one you want to minimize. And then you transform it into a different form. The first one is naive, it's just harmless. You just turn this Euclidean norm into maximization of the inner product, which is fine. There's nothing happening there. But the next one is critical. This is equivalent representation. It's exactly the same thing, but I write it in a different way where it only depends on one-dimensional statistics. So V transpose mu is a one-dimensional projected mean of the population. V transpose sigma V is one-dimensional projected variance of the population. And that's the key. And that's the critical thing, as I'll tell you. And once you've done that, then because we don't know sigma, we don't know mu, we turn it into empirical loss, but we turn it into robust empirical loss by switching out these one-dimensional statistics, not by the empirical statistics, but empirical robust ones, robust one-dimensional mean and robust one-dimensional variance. And I'll tell you exactly what it is in a bit. But once we have this empirical loss that can be computed, slow, but can still be computed, we're gonna minimize this, but we don't wanna just minimize it. We wanna minimize it in a way that it's differentially private. So how we do it is we use an algorithm known as the exponential mechanism, which samples mu hat from a distribution that's exponentially going down with the empirical loss. So you're more likely to sample that has small empirical loss and scale appropriately by epsilon over delta, where this delta, capital delta, is now your sensitivity of your empirical loss that you defined, robust one. And if you do it, it's guaranteed that this algorithm is epsilon 0 differentially privacy. But the critical part is that among all the choices you could have chosen for different empirical losses, the one we propose has dramatically smaller sensitivity because it only depends on one-dimensional robust statistics. So there's something natural and beautiful connection between one-dimensional robust statistics and how we can reduce sensitivity for privacy. And that's the fundamental connection. Privacy sensitivity versus robustness is fundamentally related in this way. And the key ingredient in showing this is what's called the resilience property of a data set or IID samples, which is a critical notion in robust statistics. So for this talk, I'll just show you how we bound the sensitivity or show you that robust statistics have small sensitivity just for the robust mean. All the others follow it similarly. So the way we define robust mean is that you project all the data points into a direction V, so it's a one-dimensional data set now. And you cut out the top 2 alpha tail and bottom 2 alpha tail. And because this is robust, it's fine if your data set has some corrupted data points, it will be naturally robust. And you take the middle part and take the mean, and that's your one-dimensional robust mean. And how we show this as small sensitivity is by using resilience. And resilience relates to the tail of the distribution, in this case, sub-Gaussian. It tells me that the 2 alpha tail on the top and also the 2 alpha tail in the bottom that you have removed, the good ones, they have mean of those tail that's not too far from the true mean, and most by order sigma v. And sigma v is the standard deviation in this direction. V is just scales how the distribution width is scaling. So it's not doing anything, just the right scaling. But it's showing you that the mean is order sigma v. And what that means is that if the average of these points is sigma v away from the true mean, and this is sigma v away, then there's at least one point, which is the smallest point in the top tail, and one point, which is the largest point in the bottom tail. And the distance between these 2 points is at most order sigma v. And that's critical because these are the 2 points you didn't include in your robust mean. This is on the tail, but they are only sigma v away. So they act as effective support because if you make one change to this data set, they will be coming into the middle set to take their place. So effectively bounding the support, which means that your sensitivity is now order sigma v over n. And this is as small as you can ask it to be. And this is the key. And once you have this small sensitivity using one-dimensional robust statistics, you can now run the full algorithm. One caveat that I'll explain now, is that this sensitivity bound only holds if your data is IID from sub-Gaussian or if your data satisfies these resilience conditions, which for differential privacy is problematic because it's a local sensitivity. Your differential privacy is supposed to be guaranteed for any data that's thrown at the algorithm. And to handle this, we use the framework from what's called proposed test release by Cynthia Dwork. But we used one that's a little bit more advanced, proposed by Adam Smith and John Woolman recently, which goes as follows. You first propose your sensitivity of your empirical loss. In this mean estimation example with a Gaussian, it's going to be 1 over n. This only depends on the tail and not the data itself, and that's the importance. And then that's the proposed phase. And in the test phase, what you do is you have an exponential mechanism you want to run. You test if that exponential mechanism with the sensitivity that you propose on the data set that you have is differentially private or not. And if it passes this test, only then you run the exponential mechanism and output this mu hat that's sampled from this distribution. Okay? To propose test release. And with this, we can show that Now we have an algorithm, and there was nothing specific to mean estimation in the recipe that I gave you, and neither in the analysis. It can be applied, to wide variety of problems. In all of this, we immediately get these guarantees, and all of them are optimal, and many of them are the first time that such a thing has been guaranteed in full generality like this, except for maybe Gaussian covariance one, I think was known. All of these are new and they're optimal. There's a matching lower bound. And there are many more we can show, just that they don't have a matching lower bound yet. For example, we can do it for Kate moment bounded mean estimation, sub-Gaussian linear regression, sub-Gaussian principal component analysis, covariance estimation. The same framework just works, gives you the optimal error rate or sample complexity. Okay, any question on the second part of which we call, HPTR for high dimensional proposed test release, because all the other existing methods only work in like 1 dimensions, not because of computation, but because of the statistical error would be huge if you apply those to high dimensions. We allow this proposed test release to be applied to high dimensional, any statistical estimation problems. Okay. So in conclusion, and some open questions, in the first half of this talk, I give you the first efficient algorithm that guarantees differential privacy and robustness both. For mean estimation with this guarantee, and for covariance estimation you'll get this guarantee. And the gap is in the third term in both. The mean estimation has gap of square root of d, covariance estimation has gap of d. And the question is there an efficient algorithm that can close this gap? Is one of the, I think, most important fundamental question. It's also interesting and practical. Those algorithms can be used in practice and give you better guarantees. And if you're a practitioner, the open questions that you might be interested in, which I am also interested in working on right now, is can we use this framework to guarantee DPSGD, differential pair SGD, is also robust? Or can we make sure that the specter, which is the defense against backdoor attacks, is also private? Is practically important question that we're trying to address. And the natural question is, can you do this beyond mean estimation and covariance estimation for things like linear regression, convex optimization, principal component analysis, and other problems? And in the second half of this talk, I gave you HPTR, which is a generic framework that gives you optimal guarantees for a variety of problems for differential private mean estimation. And the open question there would be, how general is it? Can we do it for things like structured learning, like sparse mean estimation or sparse linear regression, or low rank covariance estimation, or sparse PCA? It's not immediately, okay, we didn't have enough time to think about it yet. The paper just went on archive yesterday in time for this talk. So these are the things we're thinking right now. And another thing will be for different domains like discrete data or graphs, can you try to come up with differential private estimator of graph statistics using this type of algorithms or this type of ideas? So the first half was based on our NeWIPS paper, and this one, robust and differential mean estimation. The second half was mainly based on our recent paper that was put on archive just yesterday. So I got this number yesterday. And the first motivation about defending against backdoor attacks was based on our ICML paper, which we call Spectre. And I think this is a good time to take questions now.
Let's thank Sewoong for an interesting talk on robust statistics and then differential privacy. Do you have any questions from the audience? So I actually have a question. Do you have some ideas about, so the first, I think I understood the first half a little bit better. Mm-hmm. And do you have some idea about, for example, how to close that D1/2 gap? Actually, before that, I have a simpler more naive question. When you say the error bound that you can get runs in SVD time, I'm assuming that's singular value decomposition.
Yes, SVD is singular value decomposition. The same amount of time as you would need if you're running a singular value decomposition on the data.
I see. So that's what you mean by SVD time.
Yes.
I see. So do you have any ideas about, or thoughts about, closing that D of 1/2 gap? Since it can be achieved by exponential time.
Right. That's the next thing that we are working on. We do not have any ideas that worth sharing that has any hope yet. We just have things that we're going to try out. But I know that there are some other people also working, like Gautam Kamath is working on it, and I think he has many exciting ideas. And yeah, I am optimistic that someone will crack it in some time soon.
So you think
right
that
now, I don't have. Yeah, I don't have.
The gap can be reduced. It's not fundamental.
I am hoping that it will. Yes. But I don't have anything, that's educational guess to share with you yet. We are busy working on the second half of the talk. So
until
now we're moving back to the question.
Okay. Any other questions?
I had one quick question on that quantum score thing. It looked a bit like this method of mixtures method for bounding, sort of high dimensional martingales. Is that similar, the intuition behind using this e to the beta covariance as is it like a mixture of different directions somehow, or?
Right. So it's exactly mixing, all directions and weighting them according to this matrix exponential.
Mm-hmm.
And analytically, it's related to matrix multiplicative weights. And you use those analyses that the regret is bounded by log D or log N, and that gives you log D iteration complexity. There's something beautiful going on there. But that part is not my innovation. That's by Jerry Lee, Dong, Hopkins, and Lee. And that's a beautiful paper. If you're, for any reason, interested, it's worth the read.
Thanks.
Thanks, man.
Great. If there are no more questions, let's thank Sewoong again for his presentation. Thank you, Sewoong.
Right. Thanks. It was great seeing everyone. Bye.
Yeah. Thanks. Great seeing you.